Hi, today we are going to learn one theorem called Stokes theorem. This is my fourth lecture in this unit, and so far we learned how to find out the line integral, how to find the surface integral, how to find out what is Green's theorem, and we did some problems on Green's theorem in my previous lecture. In today's lecture, we are going to see what the Stokes theorem is. And after that we do some examples on the Stokes theorem, and after that some implications and some deductions from the Stokes theorem we'll learn. So first of all, as I said in the previous lecture also, the proof is beyond the scope of the syllabus for this theorem. So let us see the statement of the Stokes theorem. The statement goes like this. If you have a vector point function f bar which is fi bar plus gj bar plus hk bar, and it is continuously differentiable vector point function. It is continuous and also the differentiable vector point function defined on the open surface S and on the boundary C of the surface, then integral over S curl f bar dot n bar ds is integral over C f bar dot dr bar. Here n bar is the unit outward normal vector to the surface S. So in this you have a function f bar, and most importantly a open surface. For applying Stokes theorem, you should have one open surface. Suppose you have some surface like this, if it is open, definitely it will have some boundary. So this is the surface S, and this is your curve C. This is your curve C. So because S is there, this is the orientation for this curve. This is my curve C. If suppose if you have a open surface like this, then it is the boundary for this surface. This is S, and for this it is the uh, curve. This is C, and this is S. It's an open surface, not the surface like this. The sphere is not an open surface. Suppose if you take a paraboloid is an open surface. A cone is an open surface. A hemisphere is an open surface, like that. Suppose if you have a box open on one side, uh, then it is a open surface, like that. So you have an open surface. Whenever suppose if you have a box which is open on one side, the boundary, the edge on the open side is something like a rectangle. Suppose if you have a say a hemisphere, half of the sphere, then the boundary at the open surface you will have at the open part, the curve is the circle in the case of a hemisphere, like that. Similarly, if you have a paraboloid, that means half piece of a coconut. If you make a coconut into two pieces, exactly into two pieces, the one what you get is a paraboloid. That paraboloid, at the open surface, you have a boundary. That boundary is definitely a closed curve. So for applying the Stokes theorem, what we need is an open surface, and once you have an open surface, it will have some closed curve C, and this is the surface S, and this is the closed curve C, and this is the surface S, and open surface, and on the boundary, at the open surface, you will have one boundary. That boundary definitely a closed curve on the boundary C of the surface, and then you have one surface, one closed curve. Along this closed curve, find the line integral of the f bar. Find the line integral of f bar. And along this open surface, find the surface integral of not for f bar, but for curl f bar. So curl f bar is del cross f bar, otherwise you can write it. So find the surface integral of del cross f bar over the surface S, and find the line integral of f bar along this closed curve C. And if you find these two integrals are same. That what Stokes theorem says. So for applying the Stokes theorem, we should have an open surface. Whenever you have an open surface, automatically you will have one closed curve. And whenever you find a open surface integral, in my lecture 2, I have given you how to find the surface integral. There we need one outward normal vector. So what this Stokes theorem says is the surface integral of curl f bar along the open surface S is equal to the line integral of f bar along the closed curve C. Here C is the boundary of this open surface S. Anyway, the proof is beyond the scope of the syllabus. Now, if you have a surface integral over an open surface is equal to a line integral. The Stokes theorem converts a surface integral to a line integral. In the last lecture, I have given you the Green's theorem, which converts a line integral I'm just recalling that point also, line integral to a double integral. Double integral. And the Stokes theorem converts a surface integral to a line integral. So that is what Stokes theorem is. For applying the Stokes theorem, as I said, now you need to have an open surface. Open surface automatically will have a three-dimensional figure. But if I apply that, that maybe in three dimensions, you should have some surface that to open. Suppose if you take some region on a plane, I can consider that region on a plane. Suppose this is the plane, say XY plane, and suppose I have some region R. Can I consider this as an open surface? Yes, definitely we can consider this region as an open surface. And for this region, the boundary is this curve. So for this open surface, this is the boundary. In this case, what happens to Stokes theorem? Let us consider as a sub case or special case of that Stokes theorem or sub case of Stokes theorem. That is Stokes theorem in a plane. I am considering it. Suppose because I am confining only to the xy plane, suppose in place of three variables, I will have only two. Suppose the function f bar is fxy bar plus g function of xy j bar is defined on the surface which covers a region on the xy plane. On the xy plane, the surface S is which covers a region R on the xy plane. This region E is the surface for this is my surface, that too open surface. This is the boundary. So closure curve is this. Now if I apply this curl F bar, let us see what happens to that. In Stokes theorem, I have some curl F bar. I am finding that curl F bar now. I bar, J bar, K bar, and we know how to find out the curl of F bar. Yeah, dou by dou x, dou by dou z, that is the second row. Third row will be the components F, G, and 0. If I find this, if I evaluate this determinant, I bar multiplied by this is 0 and this is also 0, and J bar times J bar times and dou by dou x, this is 0 and this is also 0, and K bar times dou z by dou x minus dou f by dou y. So this is what I got here as curl F bar. Now, what is unit vector to the surface? What is where the surface is? Surface is on the xy plane. So automatically, what is your n bar for it? N bar for it will be a perpendicular line to this xy plane, which is along the z-axis. This is x-axis. This is along the z-axis, and the unit normal vector will be k bar. So n bar is the unit vector perpendicular to xy plane, which is k bar. So what is curl F bar dot n bar? Of course, I am using the capital N bar here also. Curl F bar dot n bar is, if I find the dot product with it, dou z by dou x, dou f by dou y. So what is integral over S? Curl F bar dot n bar in Stokes theorem will be reduced to integral over S dou z by dou x minus dou f by dou y ds. So while finding the surface integral, I have given you one way of finding the triple integral. In place of ds, you can write dx dy by n bar dot k bar or dy dz by n bar dot I bar or dz dx by n bar dot j bar. Because I'm only on the xy plane, I'm writing here ds as dx dy by n bar dot k bar. My n bar is k bar, so k bar dot k bar, this becomes 1, and dou z by dou x minus dou f by dou y and dx dy, sorry, this dou z by dou x minus dou f by dou y, this is the entire thing what I have into dx dy. So this is the surface integral. Surface integral s curl f bar dot n bar becomes this. Now what happens to the line integral? So next one is by Stokes theorem, integral C f bar dot dr bar is equal to integral S curl f bar dot n bar ds. So integral C f bar dot dr bar is equal to integral S dou z by dou x dou f by dou y dx dy. This S is S and R both are same. So, R E is. So I have one region R. For this, this is C, and integral over C f bar dot dr bar is equal to double integral over that region dou z by dou x minus dou f by dou x dy. This is the Green's theorem, what we learned in the previous lecture. Thus, the Stokes theorem on a plane is Green's theorem. If you this is the Stokes theorem. If it is applied on a plane, automatically it is as equivalent as for doing a Green's theorem on a plane. So this is one subcase for Stokes theorem. Let us do some problems on Stokes theorem. Just before going to the Stokes theorem, problems on Stokes theorem, just I will recall what we learned. For applying Stokes theorem, we should have a open surface. That is the first one. What we need is the open surface. Whenever you have a open surface, automatically you will have a boundary at the open part. At the open part, there will be a boundary. That boundary is the closed curve. It will be a closed curve. So, if for a open surface, always there will be some closed curve. And if you have some function f bar and find the line integral of f bar along C, that will be equal to the surface integral of curl f bar. As I mentioned at surface integral, it will also be written as curl f bar. Instead of writing dot n bar ds, I can write ds bar. This is also notation. So this is what the Stokes theorem says. And this f bar is a continuously differentiable function on C and on S and also on C. So let us see the problems first. So first problem. Verify Stokes theorem for the field. Of course, here I forgot to write J bar over the box. Though the function has no K bar, but see the surface what he has given. The surface is bounded by x is equal to 0, comma x is equal to a, and x is equal y equal to 0, y equal to b, z is equal to 0, z is equal to c, if the face z is equal to 0 is cut. If the face is cut, then it will become open. Now we have a one box. This is the box, so this is x axis, this is y axis, and this is z axis. I am naming this box the vertices O, A, B, C. This is D, this is E, F, and G, and this box is not open on these sides. This is closed, this is also closed, and this side is also closed, and the back side is also closed. The front part is also closed. The front side is also closed, but this side is open. This is z is equal to 0, xy plane. This plane is yz plane, that is x is equal to 0. And this backside plane is xz plane, there y is equal to 0. and there are other three planes. I'll call the plane x is equal to 0 as S1, and I will call this plane uh, ABGF as the plane S2, and I will call this backside, this board as the plane S3, and before front of it, the projected one, I'll call it as S4, and this as S5, and this anyway, those are the five surfaces what I have. This surface is open, we don't have the surface here. This surface is not there. This is open. Therefore, only five surfaces. Now it is a open surface. For this open surface, what is the boundary? Boundary is this. This is the boundary. So this is my closed curve. This is the curve. So here, what is my C? C is line segment OA union AB union BC and union CO. This is my curve. This is my curve. I am writing this curve separately. This is on the XY plane. This is x-axis, y-axis, and this is x is equal to A. This is y is equal to b, this is y is equal to 0, this is x is equal to 0. This is my C. O, A, B, C. This is my C. This is my surface. It contains five things. So we understood what this S is, what C is. Once you have this, we need what the Stokes theorem says, the line integral of f bar is equal to the surface integral of surface curl f bar. So I need to find out curl f bar. Find this curl f bar. I bar, j bar, k bar, dou by dou x, dou by dou by dou by dou z. These are the derivatives, and the components are x square minus y square is the x component, and 2xy is the y component, 2xy j bar, and k bar term is not there. So k bar term is not there, therefore it's 0. So find the curl f bar for it. I bar times I bar times this is derivative is 0 and this derivative is also 0. So I bar quotient is 0. J bar quotient is derivative of this is 0, and similarly derivative of x square minus y square with respect to z, that is also 0, and k bar times derivative of this with respect to x is 2y, and minus of minus, that will be plus 2y k bar. So 4y k bar is the curl f bar. And what is my n bar? N bar is what? N bar is the uh, outward normal vector. This is not same for every surface. Therefore, this is n bar is k bar only for one surface. So let us not try use it now. So curl f bar is this. Curl f bar dot n bar is 4y k bar dot n bar, 4y k bar dot n bar. So integral over s curl f bar dot n bar is 4y k bar dot n bar ds. This is my surface integral. This is my line integral. Integral over c f bar dot dr bar is integral over c x square minus y square dx plus 2xy dy, because f bar is this, f dr bar is dxi bar plus dy j bar. So dot product of this. These two I have to evaluate and have to show that those two are same. So by Stokes theorem, these two are same. Integral over c f bar dot dr bar is this. C integral over c f bar dot dr bar means this is equal to curl f bar dot n bar is this. So now we have to verify this. For verification, integral over s and integral the left hand side and right hand side both we have to evaluate. What is this c? The c is the rectangle y equal to 0, x is equal to a, y equal to b, and x is equal to 0. So this is the rectangle, this is my C. What is S? S is the surface of this surface. Already I have shown you in the figure. So this is the surface what I have. This part is open. So it has the surface S has five subsurfaces S1, S2, S3, S4, S5, and C has four lines OA, AB, BC, and CO. So let us find out those things one by one. So first of all, I'll find out the line integral. So we know how to find out the line integral. Integral C is here. It is integral over C, that is along OA, plus of course the same thing will be here also, along AB plus along BC along CO. So this equation is y equal to 0. This equation is x is equal to a. This is y is equal to b. That is x is equal to 0. First along OA. Along OA y is 0. Along OA y is 0. Then dy is also 0. So for this dy is 0, y is 0. Only thing what you will get is x square dx you will get. What are the bounds for x? X bounds are from 0 to a. Next, coming to this, along AB, x is a and dx is, this is I am doing for AB, x is a and dx is 0. So dx is 0, the first part will go out, only the second one is integral, where from along this y varies from 0 to b, and 2x, x value is a, that means 2a y dy, plus along BC, for along BC, my y value is b and dy value is 0. So second part will not be there. And along BC, x varies from a to 0, dy is 0 and x square minus b square dx plus along CO x is 0, so dx is 0, so this part goes out and 2xy is there, 2 into 0 into y into dy, therefore this is anyway 0. Let us find integral x square is x cube by 3, it is a cube by 3, and 2a integral y is y square by 2. So if I substitute 2a b square by 2, and here a to 0 is there. Therefore, if I multiply with minus, first b square minus x square I will get. For b square, integral is b square x. If I substitute the limits, it is a plus, sorry, minus integral x square is there. Integral x square is x cube by 3. If I substitute the limits, a cube by 3 plus 0. Minus a cube by 3 plus a cube by 3 gets cancelled. 2 and 2 gets cancelled. I have ab square and another ab square. Ultimately, I got 2ab square. So line integral I got 2ab square. Now I need to find out the surface integral 4y k bar dot n bar ds. Now this is equal to, I have five surfaces S1, 4y k bar dot n bar ds. Similarly, over S2, S3, integral over S4, integral for S5. So in the examination, you need to write here completely, don't write in this fashion. Integral S2 4y k bar dot n bar, here also you have to write 4y k bar dot n bar, completely write the integrand. So this is equal to this. We have to find out the five surface integrals. I think you know what what the surfaces are. So the surface, just I am drawing that figure once again here for your convenience sake. So this is the box what we have. So this is my surface S1 equal to 0. This is y-axis and this is z-axis, yz plane. X is 0 and this is my I bar, outward normal vector n bar is this, but outward I want, therefore it is minus I bar is for S1, n bar is minus I bar. Similarly for S2, S2 is this. For S2, the outward normal vector is n bar is I bar. For S3 is this board. So y, this is inside, outside normal vector for S3, n bar is minus j bar. For S4, n bar is j bar in this direction. And S5, for S5, this is my surface S5, outward normal vector n bar is k bar. So there I have curl F bar is 4y k bar dot n bar is how much? Where for all this is 0 for S1, S2, S3 and S4 because in curl F bar dot n bar I have 4y k bar I have. This n bar varies from surface to surface. For all the surfaces except this surface, for all the other surfaces, the outward normal vector is either I bar or minus I bar or j bar or minus j bar in place of this n bar. If I make it dot product with that, that will be 0. Only for k bar I will get 1. So 4y I will get. Yeah. So this is 4y dot, this is equal to 4y for S5. Therefore, integral over S curl F bar dot n bar ds will become integral 4y ds. This is my surface S4y. This is our S5. So, how do you find it? Take the projection in that the surface integrals I mentioned clearly how to take the surface integral. Now, you take the projection of this on the xy plane so that you will have on the xy plane again a, b here. Double integral over r 4y, this is dx dy by n bar dot k bar. N bar is k bar dot k bar is 1. How do you, what is an n bar, why n bar is k bar? Because for S5, n bar is outward normal vector is k bar. So this is 1. The limits are from 0 to a and 0 to b, x limits and y limits. So 4 times into y limits are y square by 2. If I substitute the limits for y, b square by 2 and integral dx is x. So this is equal to 2ab square. If you observe in previously also I got 2ab square as the line integral. So 2ab square. So the line integral value is same for both. So coming to the next problem, second one. Again we need to verify Stokes theorem for the vector. So this is the vector what he has given, and over the upper half of the surface. So what is the surface he has given? The surface he has given x square plus y square plus z square is 1, which represents a sphere, but bounded by its projection on the xy plane. What is the projection on the xy plane? Is a circle. That is the boundary. The boundary, it is not the complete sphere, only upper half of the sphere. So your, this is x-axis, this is y-axis, and you have a sphere like this, and this is the boundary. So this is my C. That C I am writing separately on the xy plane. This is a circle. What is this circle? X square plus y square is equal to 1. This is the surface S. What is the equation of this surface? X square plus y square plus z square is equal to 1. Whenever you know the surface, what is the outward normal vector n bar to it? For if you are given any surface, outward normal vector n bar will be given by grade phi. This equation of the surface, if you find the gradient for it, you will get the outward normal vector. So for applying Stokes theorem, I need curl F bar, I need n bar, I need what the surface S is, what the curve C is. Let us find out all the things. Open surface S is the hemisphere. Above the plane Z is equal to 0. Boundary of the surface is the closed curve C. Here it is a circle on the xy plane, which is x square plus y square is equal to 1. If I find the curl F bar for it, this is I j k dou by dou x dou by dou y dou by dou z And here 2x minus y minus yz square minus zy square are the components. Those components have written here. Find the Jacobian, find the determinant, evaluate this determinant. I bar times the derivative of this is minus 2yz and it is plus 2yz. Therefore, this becomes 0. Quotient of j bar is derivative of this with respect to x. There is no x here. Derivative is 0. Derivative of this with respect to z. Here also no z at all. Therefore, derivative is also 0. J bar quotient is also 0. And now coming to the k bar quotient, derivative of this with respect to x, that is 0, and derivative of this with respect to y is minus 1, because the minus of minus 1, that will be plus 1. Therefore, ultimately, curl f bar is k bar. Now, what is the n bar? N bar is the outward normal vector to the surface. The surface equation, you know. What is the equation of the surface? Equation of the surface is x square plus y square plus z square is equal to 1. This is my phi. What is the outward normal vector? Grade phi. What is grade phi? Dou phi by dou x, dou f1 by dou x, dou f2 by dou y, dou f3 by dou z. So derivative of this with respect to x is 2x, 2x I bar, 2yj bar, 2zk bar by, actually here I have 2xi bar plus 2yj bar plus 2zk bar by root over sum of the square 4x square plus 4y square plus 4z square. 4 if I take common, x square plus y square plus z square, x square plus y square plus z square is 1. Therefore 2 gets cancelled. Ultimately this is my n bar. N bar we know, curl f bar we know. What is curl f bar dot n bar? This is my curl f bar is simply k bar. N bar is this. Curl f bar dot n bar is z. Curl f bar dot n bar ds is integral s z ds. So this I need to find out. Whenever I find ds, at the time of surface integral, while explaining that topic in my previous I think it is the second lecture, I have given you a hint where to take the projection. If I take the line parallel to the zy plane, it cuts the uh, it cuts the surface at 2 points. Even if I take the line perpendicular to xz plane, then also it cuts the surface at 2 points. But if I draw a line perpendicular to the xy plane, it cuts the surface only at 1 point. Therefore, it is better to take the projection on the xy plane. If I take the projection on the xy plane for this surface, I'll get this region. This is my region. So if you take the project for finding the surface integral, I will take this region of circular region, but for finding the line integral, I'll take the circle. Circle is the boundary. Circular region is the point, is the region, is the area in between that. So integral z into dx dy by n bar dot k bar. Again n bar we know. N bar dot k bar is again z. Therefore that z and z gets cancelled. So this value we know. Now integral C f bar dot dr bar. This is my f bar. What is f bar dot dr bar? This is my f bar. F bar dot dr bar. In f bar dot dr bar is 2x minus y dx minus yz square dy minus zy square dz. This is f bar dot dr bar. These two are equal. So we need to prove that these two are equal. N bar dot k bar is also z and z gets cancelled because this is n bar. N bar dot k bar is z. Z and z, these two gets cancelled and only dx dy will. So double integral dx dy represent the area that already we learned in the double integration chapter of third unit. Therefore, this is the area of the circular region, that is pi r square, because it is radius is 1. So let us verify this. So this is where is C? C is on the xy plane, because on the xy plane this is z is 0 on the xy plane. Therefore, because of this z, because of this z, these two vanishes and only this will be remained. This, what is the C? C is this circle. On this circle, if I, what is the equation of the circle? X square plus y square is equal to 1. I need to evaluate it. I am converting that into parametric form so that it will be the x is cos alpha, y is sin alpha. If I substitute, then alpha varies from 0 to 2 pi. So alpha varies from 0 to 2 pi to x is cos alpha minus y is sin alpha into dx is minus sin alpha d alpha. If I multiply that, this will be 0 to 2 pi sin square alpha minus 2 cos alpha sin alpha d alpha. So integral 0 to 2 pi sin square alpha is 4 times 0 to pi by 2 sin square alpha. 0 to pi by 2 sin square alpha is 1 by 2 into pi by 2. This is simple integration. Minus, similarly here, if I find the integral for it, if I put sin alpha st, cos alpha d alpha is dt, and uh, sin square alpha by 2, 0 to 2 pi, that will be 0. Or even in the last lecture also, I mentioned this is a standard one where everywhere we can use it, integral 0 to 2 pi sin power mx into cos power nx dx. This value is 0. This value is 0 as long as m and n are not, both are not even. If both are even, then its value is 4 times integral 0 to pi by 2. Here 1 and 1 powers are odd, therefore that value is 0. Ultimately, this is pi. RHS surface integral, double integral, this gives the area. Area of the circle is pi r square, pi into 1 square, that is pi. So both the values I got pi, therefore the um, Stokes theorem is verified. Let us see the next problem. Third one. Evaluate. Here he is not asking us to verify. He is simply asking us to say find out the surface integral. He is asking us to find out the surface integral. Surface integral of curl V bar. He instead of F bar, he is using V bar. Finding the curl V bar. Surface integral, he is asking us to find out what is the surface he has given. Surface is the paraboloid. Z is equal to 1 minus x square minus y square is the paraboloid. Z greater than or equal to 0, that means above the xy plane, and V bar is the given. This is the function what he has given. So if I draw the figure for it, what is the surface? This is the x-axis, y-axis. This is y-axis, this is x-axis, and this is z-axis. You have the paraboloid. This is the paraboloid, and this is my curve C, and this is my surface S. So by Stokes theorem, S we know, C we know, what the surface integral value is equal to the line integral value. That's what Stokes theorem is saying. Because he is asking us to find out this surface integral, no need to find out the surface integral. It is enough if you find the line integral. That's what Stokes theorem says. And in the previous two examples, we verified that also. What is C here? C is the circle. What is that circle on the xy plane? If I put z is equal to 0, my C is, here I am writing separately, the C is x square plus y square is equal to 1 is the circle. So I need to evaluate a V bar dot dr bar. V bar he has given. What is dr bar? Y dx. Next is z dy plus x dz. This is to be evaluated along C. Where is C? C is on xy plane, on z is equal to 0. Therefore, dz is also 0. dz is 0, z is 0. Therefore, these two goes out. Only this will be remain. So, integral y dx I have to evaluate along this curve. Curve is x square plus y square is equal to 1. Now, you can integrate uh, along this curve. The y value is this x is equal to cos alpha, y is sin alpha. If I say this is sin alpha, now the parametric form of the circle is, this is not parametric, this is not the polar form, this is only parametric form. X is cos alpha, y is sin alpha. In polar form, we'll have both r and alpha, two variables. Here, only one variable alpha. Alpha varies from 0 to 2 pi. 0 to 2 pi. y is sine alpha, dx is minus sine alpha, so minus sine square alpha d alpha. If I simplify it, it is 4 times, of course there is a negative sign, minus 4 times sine square alpha is 1 by 2 into pi by 2. So 2 and 2 gets cancelled, and minus pi is the value of this surface integral. If somebody is interested and they can find out the surface integral independently, try to find out the surface integral for this problem so that you will have one exercise or one example for finding the surface integral. So find the surface integral, then also you should get minus pi. Otherwise, this result may be wrong, or your curl finding curl be your surface integral value may be wrong. So find out the curl V-bar and check it. But in fact, in the examination, the same problem is asked. No need to find out the surface integral. Only line integral is enough because he's asking that surface integral. I converted the surface integral to line integral because the Stokes theorem converts a surface integral to a line integral. Instead of finding the surface integral, I evaluated line integral. Sometimes evaluation of line integral may be difficult. In that case, we convert that into surface integral. Okay, so this in this example, that's what actually. Evaluate integral C f bar dot dr bar. This is my f bar. For this f bar, find where is the uh, curve? The curve is x square plus y square is equal to 4 and z is equal to 1.5. So you have a circle on the plane. This is my z is equal to 1.5 plane, which is always parallel to the xy plane. This is the plane z is equal to. On this plane, you have one circle. The circle radius is 2. X square plus y square is equal to 4. Now, this is my surface. Surface itself is this. Surface is, this is my surface S as well as this is my region E. This is my surface S. For this surface, the boundary is this. So, integral C f bar dot dr bar is integral S curl f bar dot n bar ds. That's what Stokes theorem says. What is my C? What is my S? S is the circular region on Z is equal to 1.5. S is the circular region on Z is equal to 1.5 plane. This is my S. So integral S curl f bar dot n bar ds. Curl f bar I evaluated. I got this. There is J bar quotient will be 0 and only I bar and K bar terms will be real. This is curl f bar. What is n bar? N bar is the outward normal vector because this is a plane parallel to the xy plane. For this also outward normal unit vector n bar is K bar. So n bar is K bar. Curl f bar dot n bar is this z cube minus 1 ds. So what is z cube minus 1 ds? I will take the projection of this on the xy plane. If I take the projection on the xy plane, this is my region E. What is z on the surface? 1.5. So 1.5 whole cube minus 1 ds is dx dy by ds dy by n bar dot k bar. What is your n bar? N bar is k bar dot k bar is 1. So 1.5 whole cube means 15 15 is 2.25 multiplied by 1.5. So it is 3.375 and minus 1. So that is 2.375 into double integral or e dx dy. This is dx dy is area of the triangle, area of the circle. Circle radius is 2. So area of the circle is pi r square, 4 pi. So if I multiply with this 4, 4 5 is 0, 20, 4 5 is 20, 28 plus 2 33, 4 12 plus 3 15, 1, 4, 4, 2 is 8 plus 1, 9.5 into pi. Or this is 19 by 2 pi is the 19 by 2 into pi is the surface line integral value. Here you try to find out the line integral separately for this C. Find the line integral of this along C. F bar dot dr bar is y dx xz cube dy minus zy cube dz. That you have to find out. In place of z, you put 1.5 and put x is equal to cos alpha, 2 cos alpha, y is equal to 2 sin alpha, and integrate between 0 to 2 pi. Ultimately, you'll get 19 by 2 pi. If instead of evaluate, if you ask to verify, then you need to do the line integral also. So this is fourth problem. So let us see the fifth one. If phi is a scalar point function, show that curl grade phi is 0 bar. So this finding curl grade phi equal to 0 bar by other means, probably you might have learned in the fourth unit. In the vector differentiation, there are certain standard results on identities of curl gradient and divergence. In that, this is one standard identity. Curl grade phi is always a null vector. That we have to prove using the Stokes theorem. Show that this using Stokes theorem I need to do. Okay. So I am taking f bar as gradient of phi. If I take f bar as gradient, let S be a open surface and C be the closed curve, which is boundary of S. S is the open surface and C be the closed curve, which is boundary of S. Therefore, by Stokes theorem, integral over S curl f bar dot n bar ds is integral over C f bar dot dr bar. Now, integral over C f bar I have taken it as grade phi. What is grade phi? Gradient of phi is dou phi by dou x into I bar plus dou phi by dou y into j bar, dou phi by dou z into k bar. Carefully follow this. Dou phi by dou z k bar dot f bar dot dr bar. What is dr bar? dxi bar plus dyj bar plus dz k bar. So what is the f bar dot dr bar then? This is integral over C. It is something like a1 I bar, a2 j bar plus a3 k bar, b1 I bar plus b2 j bar plus b3 k bar. It will be a1 b1 plus a2 b2 like that. Dou phi by dou x into dx plus dou phi by dou y into dy plus dou phi by dou z into dz. Now, dou phi by dou x into here, most importantly, this is the closed curve. So just to remember that, I am mentioning like this. This is a closed curve. Don't forget that point. That is more important. So what is dou phi by dou x dx, dou phi by dou y dy plus dou phi by dou z dz from your partial differentiation topic of first semester? This is equal to d phi, total derivative over C. Integral d phi is phi. Okay. Because it is a closed curve, for a closed curve, if A is a point, starting point, again you come back to A only. So starting and ending are the same for that curve, phi d phi. Integral d phi is phi, the up between A to A. Phi at A minus phi at A, that is 0. Therefore, I got integral over S curl f bar dot n bar ds. I got 0 because there is dot product. Ultimately, I got a value 0. Therefore, this is 0. N bar is never be 0 because if you have some surface at different points, you will have different normals. This is never be 0. Therefore, only possibility is this is a 0. That is 0 because it is curl f bar is always a vector. It is a null vector. 0 bar dot n bar ds. This is becoming 0 means this. Curl f bar dot f bar is 0. Therefore, curl grade phi is always a null vector. That is what. What is my f bar now? F bar I have taken grade phi. Therefore, this is curl grade phi is null vector. This is the proof of this result. Now, it's a very important topic. So far, from your fourth unit, you learned vector is said to be irrotational if its curl f bar is a null vector, it is irrotational. And from this Stokes theorem, we'll derive another two, three results. So some deductions from Stokes theorem, let us see. Suppose f bar is an irrotational field. Keep that in mind. F bar is an irrotational field. Uh, then we know that because f bar is irrotational, del cross f bar, of course, this is not this. Del cross f bar is a null vector. Del cross f bar, curl f bar is null vector. This already you learned at your then fourth unit. What the Stokes theorem says? Integral S curl f bar dot n bar ds is integral C f bar dot dr bar, where C is the closure curve. Therefore, integral C f bar dot dr bar is integral S because f bar is irrotational. Curl f bar is a null vector. If I integrate, this will be 0. Integral C f bar dot dr bar is 0. So from this part, and previously I solved one problem here, fifth one. So the proof from these two, what you can understand is here, if the line integral is 0, then curl f bar is 0 bar. That is the conclusion what I made. Here, when curl f bar is 0, curl f bar is 0 or del cross f bar is 0, here I proved this line integral is 0. So that both of the things are correct. So that is from the Stokes theorem. So whenever you have an irrotational vector, you have one result that it is curl is 0. And if somebody one day you say that the vector is irrotational, now your answer can be two ways. One is curl f bar is 0 bar, that is one answer. Second answer is the line integral of that f bar over a closed curve. If you take a closed curve and if you find the line integral for it, if you get 0, then also it is irrotational. And one more result I am deriving. From the just now I proved curl grade phi is 0 bar. This is whatever phi you take for any phi, whatever scalar point function, phi is a scalar point function, whatever scalar point function you take, for that find gradient, after that find curl, this is always 0. So this is one result. If f bar is irrotational, curl f bar is also 0. So observe these two. Del cross f, of course, this is del cross f bar is 0 bar and curl grade phi is 0 bar. From these two, this f bar and in place of this grade phi both are. Therefore, if f bar is irrotational, then there exists a phi, there will be one scalar function phi such that f bar is equal to gradient of phi. This phi is called a potential function of f bar. So you just read the red letters and if f bar is irrotational, I am putting a tick mark here. If f bar is rotational, curl f bar is 0 bar, that is one thing. The line integral of f bar along a closed curve is 0 or the circulation of f bar is 0. Second thing, third one is f bar can be written as gradient of phi. So we can understand or we can notify or we can identify a irrotational field in three ways. Either by finding curl f bar and show that it is a null vector, or find the line integral along a closed curve and show that it is 0, or else observe whether there is any scalar function phi. For that, if you find the gradient, then gradient of f bar is 0. then what is this phi? If such a function, if f bar is given to you, if you can show that it is equal to grade phi, then this f bar automatically becomes an irrotational. This phi is called the potential function. Let us see another interesting result. If f bar is irrotational field, so far we learned 3 points and extension of that. If f bar is irrotational, then what is that we learned previously? The line integral over a closed curve is 0. So if this is a closed curve, if along this closed curve, the line integral over C, if this is C, that f bar dot dr bar will be 0 if will be 0 for a irrotational function. If I don't take the line integral, if I don't take the closed curve, if I don't take the, suppose if I take this curve, and the starting point is say P, the end point is Q, and if F bar is irrotational, if from P to Q, if I find the F bar dot dr bar, definitely you don't get 0 because it is not closed. If it is closed, you will get 0. There are 2 points. Suppose if I take another curve which joins these two. From P to Q, for this curve also you will get some other value. If I take another curve joining the same points PQ, then also I'll get this line integral some value. But the thing is, if f bar is irrotational, the whatever line integral value, that is always same. The line integral value is always same. That is the theorem. If f bar is a rotational field, then the line integral between 2 points P and Q is independent of the path joining these 2 points. Whatever path you take, either this path, or this path, or this, whatever path you take, for any path, the line integral value is always same. If it is same, how much is that? And again, go back to A previously. If f bar is irrotational, I said there will be a potential function. And that potential function at the end point Q and potential function at the starting point P, that difference is the line integral value. That is, this says. So this is similar to the fifth example what I have proved previously. Let's see the P or QSP. This is P is one point. This is Q is another point. This is P. So I have taken one P or QSP. This is the closed curve. This is another point R. This is another point. So this is one curve and this is also curve. So PRP is one, PRQ and QSP. Be a closed curve. This is the closed curve. Since f bar is irrotational, what I just proved, the line integral over this closed curve is integral over C f bar dot dr bar is 0 bar. But what is this closed curve? It is the curve PRQ plus the curve QSP. So some other closure curve is union of these two curves. I'll bring this on this side. So PRQ, FDR, QSP in this direction. If I move the direction the reverse way, PSQ if I write, then negative sign will go. QSP, and I have written in the reverse way, PSQ, then this is equal to this. So you observe these two. This is PRQ means from P to Q along this curve. This is also from P to Q along this PSQ. Both the line integral values are same. That's what I proved. Therefore, if you join 2 points along any curve, the line integral along that curve is same whenever that point f bar is irrotational, not for every time, only when the function we are taking is irrotational. Now, since f bar is irrotational, just now I proved there is a potential function that f bar is grade phi. So what is your f bar integral f bar dot dr bar? In place of f bar, I will write grade phi because f bar is irrotational. That is always equal to gradient of phi. So gradient of phi, this is the definition. This is dr bar. Dot product is this. This is d phi. So grade phi dot dr bar is d phi. So integral p to q, grade phi dot dr bar is d phi, and phi at q minus phi at p. which is the potential difference between these 2 points. So if f bar is irrotational, then uh, my if f bar is irrotational, the line integral joining any 2 points, the line integral joining any 2 points, so the line integral joining these 2 points along any curve is always same, and it is equal to phi b minus phi a. So with this, I am finishing my present lecture. The next lecture will be on Gauss divergence theorem. Prior to Gauss divergence theorem, I'll um, I'll start with the problems on this last topic. That is, if f bar is irrotational, what is its potential function? How to find out that phi? I'll solve one or two problems on this topic also. After that, I'll move to Gauss divergence theorem. Before going for Gauss divergence theorem, I will define the volume integral, and after finding volume integral, I will find the Gauss divergence theorem. Okay, this is what Stokes theorem is. For applying Stokes theorem, remember we need a open surface, and at the open part there will be the boundary for it, that will be a closed curve. The line integral of any function f bar along that closed curve is equal to the surface integral of curl f bar. That is what Stokes theorem. We observed certain problems. I think the Stokes theorem is very clear for you.